Okay, we have a problem in physics in energy, specifically the work done. We have a crate that is being pushed or pulled with a force and angle of 30 degrees, a force of 155 newtons. Okay, and so this crate is being pulled 30 meters with a rope at that angle. And what we want to do, we want to find out a couple things. We want to find out what is the frictional force of the system. Now, if the brick or the crate was in equilibrium, it would not have an applied force, and mg would be equal to n. In this case, we do have a frictional surface, and we have a mu of 0.450. So we have to take this into consideration. So if we take the tension vector of 155 newtons and divide it into its x and y components, we have Fy and Fx. F of x is going to be doing the forward work. Okay, F and y will not have an effect unless there's friction, and there is friction. And this is going to cause a lifting effect that is actually going to make the crate a little bit lighter in weight. And so that's going to add to that change in friction. And so how does that change it? Well, it changes it, if we look here, we know that a frictional force is mu times the normal force. But we have to make a change because we have, here's our weight, m times g, minus the force times the sine of 30 degrees. This is the F of y vector that's creating this lifting effect on the crate. And so that is going to actually eliminate some of the frictional force. Okay, and so let's calculate this out. We have the frictional force is going to be equal to mu times n. N is going to be equal to this right here, so we'll plug everything in. We have mu 0.450. We have the mass times the acceleration of gravity minus the force times the sine of 30 degrees, which is 0.5, and we get 53.3 newtons. So that is answer to the first one. What is the frictional force? And this frictional force is acting in the opposite direction of movement, which it should be if it's friction. B, find the net work done on the crate. And so the net work is going to be, after we take away the work, the non-conservative work, which is caused by friction, we take that away from the total amount of work that's being done by the work done on the x-axis, okay, we're going to get the net. So let's first figure out what is the work done on the x-axis. And this would be this vector here, or we can look over here, f of x, okay? And f of x is equal to f cosine 30 degrees. So we're going to plug this into the work done equation, and we get 155 newtons times the cosine of 30 degrees, 0.866, times 30 meters, and we get a grand total of 4,027 joules. So this is the total amount of work that is being done by the rope, less the frictional force in the opposite direction. So the frictional force here, we need to find the amount of work, and this is non-conservative work. It's going to be times the distance moved. So we've already calculated the frictional force, 53.3 newtons, times 30 meters, and we get a frictional force almost 1,600 joules. I'm sorry, a frictional energy of 1,599 joules. Okay, so with these two, we just basically take the difference. And if we take the difference, we're going to find the net work done. Okay, and so here we plug them in from this equation right here. And we have a total work done of 2,430 joules. So, C, what is the energy loss? Okay, well, we know all the energy is lost due to the frictional force, okay? So it's just basically taking that frictional force times the distance or displacement that the crate travels. And so we've already calculated the frictional force, 53.3 newtons, times the 30 meters, and we get 1,599 joules, which we actually calculated right here too. So we answered, by doing B, we answered question C.